And then let's go. So today we'll talk a little bit about the legal frameworks related to nuclear safety. These legal frameworks can be, in principle, they might require a lot of detailed explanations. We'll not go there. We'll just try to give you a feeling what must be set in the law when we are dealing with nuclear safety and nuclear materials. And then we'll have some examples how it is really set in the law. Most of it you will do in your seminars, trying to figure out certain things in the legal texts. That would be, I guess, a nice exercise for technical people or science people to try to figure out what the legal people think. Well, you know, why are we doing this? Things are becoming more and more complex. Technically and in the society, things become more and more complex. So one of the consequences is that people usually specialize more and more and more in some details, and they need advice of somebody else to complete any task. It is kind of interdisciplinary. And if you are working in the interdisciplinary environment, then you have to somehow understand at least a little bit.
Leon, I'm sorry to interrupt you, but we have a black part of your slide is black. Lower in the lower left corner. I see others also have the same problem. You and Professor Mauko.
Good. Nice that you say that. Something is being, now it's better.
Now I don't see the slide.
Yeah, I understand that. But the problem with the blackout is done.
Yeah, this is it.
Okay.
Thank you. So the guys at home had a partial blackout of the screen. Blackout is if there is something black in the nuclear power plant. They say blackout when there is no electricity. What do you think about this no electricity in a nuclear power plant? Is this good news or bad news? But it's strange. You are in the machine producing electricity and you are lost if you lose the electricity. How come? Yes, I'm still trying to put you into the perspective. Okay, you are there having a large machine to produce electricity, and if it does not produce electricity, you're in trouble. Wow, that's a little bit strange, but it's one of the reasons, yes, for the nuclear safety. In any other case, any other type of power plant, if you lose the electricity, it's not a big deal. Although sometimes, let me also share this part of the information for you. Sometimes if there is a large blackout, so if, for example, that the power lines would fall apart, then all the power plants have to stop and then you have to restart it. Not every power plant can start without outside electricity. Needs to be specially designed for that, for a black start. We have one gas plant in Brestanica in Slovenia, and another one is hydropower plant, one on Drava River. I don't know which one. They can start, and then you supply some electricity to the grid, and then the others can start. Nuclear power plant, by the way, in Krško, when we are starting with blackouts, they produce about 700 megawatts of electricity, but they internally need nearly 40 megawatts of electricity to run all the pumps, all the stuff. So in principle, you need 40 megawatts to start it. Okay, we'll touch the legal frameworks for nuclear safety. Mainly, this is our core business, nuclear safety here. We'll touch a little bit nuclear security, a little bit nuclear safeguards, just to have a feeling. And we'll try to connect this legal stuff with the technical information you already have on the nuclear power plant. I hope you have some idea how it works. So let us repeat the definitions. Nuclear safety is to protect people from the nuclear materials. Nuclear security is protect nuclear materials from people. And safeguards is prevent the use of civil nuclear materials in the military explosive devices. Okay. Now, if you would like to talk about the legal framework, then you have to say, okay, there is a state, a country or state, and there is a government or something like that, and they have to produce somehow the legislation, the legal framework, the legislation. If you would like to talk about nuclear safety, then it's a good idea to say when the country becomes a nuclear country. Not every country is nuclear. Now, is Slovenia a nuclear country? Yes. Is Croatia a nuclear country? No. You are coming from which country? Jordan. Is Jordan a nuclear country? There is a research reactor already. And you? Egypt. So is there any nuclear installation there with the fuel? Research reactor. And you? Not a nuclear country. Yep. Now, the responsibility for the legal framework and for the safety as such is with the state, represented by government. Usually, government is the executive branch of the state, and they need to have a nuclear installation. And nuclear installation is something which is land-based, so it's not a ship, must have a civil use, not a military use. Military is out of our scope here, and needs to have nuclear fuel elements in the plant or close to the plant. As long as there are nuclear fuel elements in the country is nuclear country. If you have spent fuel, you export it or store it in the long-term storage. Long-term storage could be a tricky business. That's for the lawyers to decide. But if you can export the fuel, that's it. It's not a nuclear country anymore, okay? Okay, it says it can be stored safely, so then you're not a nuclear country anymore. Good. So to be a nuclear country, you need an installation, and this installation needs to have fuel. Okay. We said that the nuclear safety is the business for the local government, for the state, for the country. But there are international discussions or international rules what needs to be done in terms of nuclear safety. Why would that be so? Why do you think it's good to have an international idea or international agreement what to do? Well, it's still, we'll see to that. It's still the decision of the Slovenian parliament. So there is only international guidance. We can decide whatever we want in principle. In principle, it's not a good idea probably, but we can decide whatever we want. One of the reasons is that actually when you have the accident in a nuclear power plant, the radioactive materials, especially those in aerosols and gaseous conditions, can go to the neighboring countries. So in Slovenia, what do we have? You have an idea how far the country border is away from the nuclear power plant? Sorry? Less than 20? About 10, between 10 and 15, I would say. And what was the let's say, the size of evacuation around Fukushima? Anybody has an idea? How many? 25? So, and Zagreb is 40 kilometers away from the Krško nuclear power plant. So there is a good idea to have some international rules how we behave. Which is the next closest plant to Slovenia? Well, the first one in the which country, which place, distance, who knows? The closest one. Czech is a little bit far away. Hungary, Paksan in Hungary is closer. And there are 4 Russian VVRs there, and they are building 2 1000 megawatt VVRs now at the moment. They started the earthwork. So it's 200 kilometers away. Okay, so in the international domain, we have the Convention on Nuclear Safety by the International Atomic Energy Agency, which actually most of the countries signed. So the legal business is they propose a text, and then in Slovenia, for example, the parliament would say, okay, we are happy with this text, and they did. So we are happy with this text, and it is then kind of a law in Slovenia. The second one is also on the safe storage of waste, nuclear waste, which will not touch very much because it repeats most of the interesting things. Then European Community, and this only goes for the members of the European Community. We have one of the basic treaties from the year of 57, Euratom Treaty. Euratom tackles nuclear safety, tackles safeguards also, will touch the safeguards. And it's one of the basic treaties of European Community. When Slovenia joined European Community, again, the parliament said, okay, we accept the Euratom Treaty. So we are part of this, and it's a law in Slovenia. It has the power of the law. And then there are 2 directives on establishing community framework for the nuclear safety and establishing community framework for the safe management of spent fuel, which are a little bit lower level documents than Euratom Treaty, but still they have to be not directly taken in Slovenian system, but implemented. So our regulation or our laws cannot be much different or not different they cannot go against these rules. We have to be within these rules. We'll touch a little bit where it goes. Let's go down. Okay. And the conventions of the International Atomic Energy Agency and Euratom define some essential elements. What are the parts the national regulatory or legal framework needs to have? The first one, again, my PC decided not to go ahead. Let me try to trick it out. We share it to the screen in the lecture room. Okay. So, as we said, it's the business of the Slovenian state or Jordan or Egypt or Guatemala to figure out what is the safety requirement in this country, and also to provide appropriate regulations to describe this, what is safe and what is not safe. Usually, you know, in the historic developments, like the United States were the first with the nuclear power plants, exporting them around. So countries tended to look into how these things are done in the United States, and they copied, and even we copied how the things were done in the United States. And we are still in somehow between the system or the thinking in the United States today and the thinking in Europe. And thinking of International Atomic Energy Agency could be a little bit different because, of course, of the Russian and Chinese influence, and they have to agree all together what is important, what's not important. Then the second basic rule: if you would like to run a nuclear power plant or nuclear facility, you need to have a license. You need to get a license and need to have the license. Let's compare it to the car. If you would like to drive, you need a driver's license. If the car also needs a license, okay, that type of thinking. And if you would like to get the license, there is a set of rules and knowledge and things which you need to show before you get the license. The country has to define who does what, responsibilities, and separation between different government agencies. So there are usually government agencies which promote the use of nuclear power. That would be the, let's say, Directorate for Energy. If you would like to have a lot of energy, there is somebody who promotes different sources of energy. But to the other side, there is usually a regulator who needs to keep watch on the safety. So in principle, they don't care if you can produce the electricity or not. They care about the safety. And they have to be separated, not to come into something called conflict of interest. You heard this before. What is a conflict of interest? Okay. That's a conflict of interest. If you work for the regulator and at the same time you work for the utility company or something like that. But who is familiar with the story of the American airplane Boeing 737 MAX? This is the one, they fell down maybe 2 or 3 times, and then there was a big investigation into the regulatory process. The technical issue was somehow they had larger and stronger engines. So the airplane became kind of unstable. Usually if you fly like this, you have better attack angle and better upward force. How is it called? Sorry? Not the climb rate, the force keeping the flight, the airplane in the lift. So in this case, because of the bigger engines and stronger engines, it was kind of sensitive. If you would increase the attack angle, then it will start to be aerodynamically unstable because it will try to go up. So they solved the problem with software. There was a software trying to put nose down. And because it was not really thought through very much, at the end, the airplanes were falling down even in great, nice weather because pilots couldn't override the system, the software. And one of the nice comments with the conflicts of interests involved was by the CNN at that time. So there is a Federal Aviation Administration, which is a regulator in US for the aviation, and they didn't have enough people, so they relied on retired Boeing people in the regulative process, which is a conflict of interest. And the comment of the journalist was, so Boeing was supervising Boeing to help Boeing sell more planes, and they also, it's still not solved today completely. So it took them now, I think, about 2 years already to try to solve the problem, still not there. Okay, the next one, which is a little bit also connected to this story. The primary responsibility for safety is always with the license holder. So even if Boeing did a bad plane, it's still the pilot who needs to fly it. Okay, it's the pilot who would have to, and of course the airline behind him, the company behind him, who should be able to figure out this does not work. Okay, it's like you are in the car. Doesn't matter if it was repaired bad or if it's old or if it whatever. It's you as a driver, or bad weather. Everything goes on you as a driver. That's the kind of primary responsibility for safety. So the license holder is usually the guys operating a nuclear power plant, or the company doing that. There needs to be something called competent regulatory authority. And this should be completely independent from promoters of nuclear energy. These are the guys who put together the rules. So the safety requirements, the regulation, they look if they are obeyed, and they also enforce if there is a problem. So they're in the same, if you go to the traffic, enforcement is by police, inspection is by police, okay, usually in the traffic conditions, but the rules are not necessarily written by the police. Here they are written by the police. They might have different departments though doing that. Okay, in Slovenia we have two regulatory bodies. We'll touch the reasons why. But one is more for nuclear safety and radiation damage in the environment, and the second one is more for the radiation damage in people. So one is in Ministry of Environment, another one is Ministry of Health. Okay, the governments need to take care that there are adequate financial resources, especially financial and human resources to fulfill all the safety tasks. Human resources, it goes for education, training, and to figure out what the human capabilities and limitations are. We are not perfect. We cannot do everything, nobody of us. So somebody, this is also an element of nuclear safety. What people can do and what they cannot do needs to be taken into account at some point. Radiation protection, emergency preparedness needs to be taken care of. Let me say that emergency preparedness is usually not done or not really led by the competent regulatory authority. Emergency preparedness is between police and military. It's done by the government. So if there is evacuation, it's not done by the plant staff. It's done by the military, or we have civilna zaščita in Slovenia. It's kind of, they belong to the military, but they are not military, okay? They help in the natural disasters. The legal framework needs to be reviewed regularly because there is developments in science, developments in technologies, developments in operating experience. Like after Chernobyl, they revamped a lot of things. After Fukushima, they also revamped a lot of things. This was the operating experience part of the story. For the science, they are usually not so keen to change something. And European Union, that's kind of specific, but it's being taken also on board with the IAEA. European Union wants to have periodic safety review. So the license holder needs to redo the assessment to look if the plant is still okay every 10 years. Okay, now how would the safety goals, what do we want to achieve, look in the high-level document? This is the European Safety Directive from 2014. So the European government says member states, not we, member states, you have to do it. Okay, so it's a message from the Brussels. not we, you. Member states shall ensure that the national nuclear safety frameworks requires that nuclear installations are designed, sited, constructed, commissioned, operated, decommissioned with the objective of preventing accidents. Smart. And should an accident occur, mitigating its consequences. And mitigating, you know what it means, so try to make consequences smaller, at least. And avoiding early radioactive releases. So early means before you can organize evacuation, for example, and large radioactive releases. So large would mean where you have then permanent trouble with the land, which has been touched with the radionuclides. So the member states shall also ensure difference actually between the old installations already in operation and those which received license after 2014. Not very many in Europe, by the way, and none in Slovenia. We only have the one which is there for a long time. But okay, in principle, requirements for new installations are a little bit higher. Now, for the old ones, yes, for the old ones, they need to do everything which is reasonably practicable to get all the new safety features on board. Now, what is reasonably practicable? Yeah, but it's possible, so it could be reasonably practicable. What? It makes no sense. Okay. Well, I was pushing it, so the seawall at Krško would be, in my view, reasonably practicable. It could be done, but it makes no sense. Now, who decides what is reasonably practicable? Actually, so the first one is the licensee, the guy having the operating, to operate the plant. They can decide it makes sense financially. They will not invest in something where, in principle, where they will not get the money back. So they can decide to shut down the plant. That could be a reasonably practical solution. And then in the second round, of course, if they propose a solution, the regulatory body would decide if the solution is okay. There is another article which actually says we need defense in depth approach to safety. We'll discuss this a little bit more in detail in the second hour today. And defense in depth should ensure that impact of extreme external natural and unintended man-made hazards is minimized. The intended ones go to security, by the way. Unintended are safety. So that is minimized. Then there is something which is called this is the formalized part of the defense in depth, to prevent abnormal operation, to keep all things normal as long as possible. The first level. The second level, if operation goes out of normal, then we try to put it to figure it out and put it back to normal. That's the approach. Do you have any idea what would be this in real life? Shutdown could be a solution. Yeah, that's one of the solutions, if you can shut down. Now, if you cannot shut down, well, still in the next one, the accidents, which were thought of during the design, they should be controlled. Something like that. But then, eventually, you will lose control. That's the next level of defense. If you lose control, then you have to be able at least to prevent big consequences or mitigate big or large consequences. This is the Swiss cheese model of defense in depth. So imagine you have different layers. If the first layer is broken, then the second layer will stop. And then you have maybe 3, 4, 5 layers to be nearly sure that things will be contained. We'll touch the details of this a little bit more later. And there is one additional requirement to promote and enhance effective nuclear safety culture. We'll spend maybe next week or by the end of the month some time of the nuclear safety culture, but it basically involves behavior of people, which is focused on safety. The movies, the Whiskey Romeo Zulu and the Chernobyl series are about this type of safety culture, how the behavior of people in the company and individuals can ruin. And so it's in the law. You have to take care of it by management systems to register what's going on and analyze if there are any troubles elsewhere. The operator has to be aware of it. And if they have any problems in their own plant, they have to report to the regulator. And last but not least, education and training. I don't know why it's always the last one, but okay, it is there. This is also that the directive puts into place, there must be a license, and there must be at every 10 years of periodic safety review. Now let me comment this a little bit. If you look at this first A part of the licensing, you would see that license is always specific to the site. So license for Krško site would be different than license for Ljubljana site, in principle. It's different for different machines. Different countries with regulations. Now, in some European countries, it's even more diverse than the country. So in Germany, the regulations would vary from land to land. From Bavaria to Baden-Württemberg, there will be a different safety rules. In Switzerland, the safety rules would be different between cantons, okay? So license is always specific to that. 3 factors: site, machine, and country where you do it. That's why the nuclear vendors try to be very unhappy, because they need to adapt the machine to a specific location, specific country. In airline safety, that's not needed, actually.
Transfer license from the European country makes it easier, right?
Yes, there is a lot of discussions about the transfer of license to make it easier, but it's not yet there. It's still the sovereignty of the state, so everybody can do whatever they want. Okay? And the regulators, in principle, they will lose part of the power or part of the sovereignty if they would adopt the license from anybody else. Talking to European guys, they are not very, very keen. Even a European license is not yet there. Not even close. Okay, the second one, also installed here by the European Commission, is periodic safety review. You have to do it every 10 years. The American approach is do it continuously, all the time, not only every 10 years, okay? So there was a little bit of debate, which one is better. If you are, I'm more in favor of continuous. But from the let's say, inspection checkpoint, it's easier if it's done every 10 years. Then somebody brings the documentation, says, I did it, you can look at it. And continuous requires work all the time and checking all the time. Now, more specific safety goals with numbers or something like that would usually be in national legislation. the international legislation, they don't want to tell you what to do. There are some guidance documents, but they don't really want to tell you what to do. You can decide on yourself. That's also one of the basic reasons why the joint license is not yet there. Okay, we need to spend some more minutes on the hierarchy of national legal documents. So let's look into Slovenia, US, for example. That's two examples. You can then go for your examples in your country for the seminar if you would like to. So Slovenia needs to obey the Euratom Treaty, the Convention on Nuclear Safety, and also the Euratom directives. For us, this is obligatory. For US, the Euratom, the European documents are not. They don't really care about this, but they did endorse the safety convention of the International Atomic Energy Agency, so they have to do it. Then in Slovenia, we have a very, very high-level document, resolution on nuclear and radiation safety, where the generic policy is specified. It's 20 pages document. If somebody is very keen to read it, you are welcome. In Slovenian only, sorry. Maybe there is a translation. I can check. And this is not really an executive document. It's a kind of the goal-giving document. Executive document is the law act on ionizing radiation protection and nuclear safety. And in US, they also have the Code of Federal Regulation number 1050 is for the licensing of nuclear power plants. Then we had a lot of lower level acts in Slovenia. Again, one is governmental decrees where the government says this is done in a certain way. Then there are rules. Rules are issued by ministers, not by the government. Somebody of you would probably look into this for the seminar, how this is done. And then still the decrees and the rules need to be obeyed. It's still the legal text, which it must be done in this way. And then you have regulatory guides, which are also present in the United States. This is only a guide from the regulator, okay? So the regulator says, this is how I see things. If you do it this way, it will be faster. I will review it faster. If you do it any other way, I'm happy with this, but it may take a lot of time to understand what you did. And then there is another, a little bit lower level document, which is issued in Slovenia by the regulatory body. And this is the decision, and it has the power of the license, okay? They decide you have a license, and in the license, they tell you what to do and how to do. And then if you change something, you go for a change of license, like with your car, if you change the engine, you have to go for a change of the license of the car. Also, the Americans, they have something called license. And license is then the document which is taken by the nuclear power plant to do it. There are different industrial codes, cookbooks, how to do things, how to design a pipe, how to design electric something, which are in Slovenia non-existing mostly. We use mostly American because of American nuclear power plants. And by the way, in the United States, at least the boiler and pressure vessel code is as a cookbook how to design boilers, pressure vessels, pipes, is endorsed by the law. They tell you, you have to use that. Or if you use this, it's okay. Now, the international documents, whatever the International Atomic Energy Agency has, is guidance. They tell by themselves, please use national regulation first. That's the priority number one. If the national regulation does not solve your problem, look at the country of origin of your technology. If that doesn't bring you to a solution, you may look at the IEA guidance. I'm still using the IEA guidance for most of the words and concepts because the concepts are more or less the same all over the place, just to show you how it's done. Now, you can imagine that there is plenty of guidelines, but not very many of laws. So this is how the documentation gets spread around the place. Okay. We'll touch a little bit upon the licensee and its primary responsibility for safety. The text in the convention is each contracting party, which is a country, shall ensure that prime responsibility for the safety rests with the holder of the relevant license and shall take the appropriate steps to ensure that each such license holder meets its responsibility. So it kind of gives the power to the regulator to give you a license and to check if you are working along the ideas of the license. Good. What does the regulatory authority do? The main functions are to prepare regulations and guides. The second one is to review the safety evaluations. So it's the licensee, the nuclear power plant, who proposes changes, but the regulator has to review and assess and approve or disapprove it. And they are involved in inspection and enforcement. What is enforcement? Do you have an idea? Inspection, probably it's a close call for most of you, but what is enforcement? Shut down the plant. Yes, if you're driving, what would the enforcement be then? You get a fine, or you can get also taken to the prison if you are too drunk, for example, in our country. You can go away. And it's the regulatory authority who needs to inform the public about the questions of safety, because they actually represent us, okay? Us, if we put ourselves now in the position of general public, it's the competent regulatory authority who is taking care of us against the guys running the nuclear power plant. They need to do a few things. They need to understand the legal, technical, and regulatory business. And it's pretty tough job, by the way. It's not very easy, so they need to be personally efficient. And then is one more thing I would like to say about the regulatory authority. They cannot give away their responsibility. Even in case that they hire some support or some advisors or they sometimes call it technical support organizations, they are responsible for the final decision, okay? Again, if you go to the driver comparison, whatever your guy sitting on the next seat tells you, doesn't matter, you are driving, okay? You cannot give him the will to drive, you are driving, you are responsible. Advice is nice, but not really there. So we have two regulatory authorities in Slovenia. That's not necessarily the case everywhere, but sometimes it is. One is for nuclear safety, radiation protection, especially of the environment, with the Ministry of Environment, and another one is Radiation Protection Administration, which takes care of the people. We mentioned that it's part of the Ministry of Health. The director of this one will talk to you about the radiation protection in about 1 month time for a while. Okay, this one I can skip now because you will have it in the materials. It's how this words early release, mitigate, prevent are used in different by different international organizations. Now, few words about the nuclear security. It's physical protection of nuclear materials. What we do is this is designed to prevent, detect, and respond to criminal and other activities related to nuclear or radioactive materials. Here, nuclear is usually meant in the fissile material, and radioactive everything else, and associated activities. So it's against terrorism, against crime, against. It's again national regulation which is needed here. It's no international. It's international guidance, but the state, Slovenia, has to do it by its own, or by our own means. For the nuclear safeguards, it's, as we said, to verify that nuclear facilities, civilian nuclear facilities, are not misused in, and nuclear material not diverted from peaceful uses. Okay. This one targets fissionable materials and related technologies and equipment, not all the dirty bombs and stuff like that. I will just point out that we have a civilian limit of low enrichment of uranium. So in civilian use, you can only go up to 20% of uranium-235. In military use, they go up to what's nearly 100%, about 75, 95, 97. And while everything which is above 20% is high enriched uranium, still the weapons grade, for your information, is 85 or higher. So there is ample margin, but still, this is not the national responsibility. It's the international inspection. Enforcement in international law is not really there, but it's international inspection to try to figure out what you're doing with these materials. Okay. With this, I would close, give you, the slides are already on the webpage of nuclear safety subject. So what I would like you to do for the next Tuesday at 12, each of you pick up, for foreigners, please look into your country. Are there two from the same country maybe, or you're okay, perfect. And from the guys from Slovenia, can you coordinate a little bit to cover it around? So you will not, just a little bit, not to that everybody will not talk about the same thing. Try to make, do you want, can you coordinate alone, or do you want me, or to, you will manage, perfect. So try to be within 5 minutes, which means 3 slides, perhaps something like that. Yeah, well, it is already on the website, but you can. No, it's open website. I will send you the link to the website. It's free. This one is free. Okay. Then we can have a few minutes of a break. Let's say 10 minutes of a break, and then let's continue in 10 minutes. So, okay, we go. Do you hear me, guys, in the office?
Ja, vas slišimo.
Yes,
Perfect.
yes.
Perfect. So we are there. Okay. Let's now continue with some concepts of nuclear safety. We'll not complete the story today. We'll have to continue next time a little bit, but still, let's try to do the best. again, I have a frozen screen, which is not a very good news. This one is much better now. We'll touch a little bit on what would be safety goals, and then we'll go into defense in depth from two viewpoints. One is kind of historical one, multiple barriers for radioactive materials. That's how intuitively the first designers came to the defense in depth. And then it was formalized. This defense in depth was heavily formalized in the last years, last maybe 20 years in different international environments. Then connected to that, we'll go into plant states. So plant states somehow correspond to different levels of defense in depth. And we'll put a list of the major safety design principles today together, and then we will discuss it further next week in more details to give you an idea how we try to defend, to actually design a machine which behave in a resilient way. So whatever goes wrong, it somehow tends to correct this by its own as far as possible. So the safety goals. Remember, it was control, prevent, and mitigate. Control the normal things and prevent and mitigate the accidents. And there are two really important accidents at the end of the story, which you would like to prevent or you would like to prevent. First one is the core melt. And the next level, if you have the core melt, then you can go in the large release of a large or early release of radioactive materials. And now let's see if we have at least some probabilistic numbers, what would be expected or, let's say, accepted frequency of such an event. So for the second generation of nuclear power plants, Krško being one of them, so built within the end of 60s to nearly 2000, the core melt is estimated to be there in once in 10,000 years, operational years, reactor years for each reactor. So the unit is per reactor year here. We have, let's say, with all the reactors on the planet, we have maybe 40,000 years of operational experience. And we had a few accidents, so we are probably really in the range of 10 to -4 or a little bit more even. For the new plants, so if there will be a next plant, they will have to show to be one level better, one order of magnitude better, so 1 in 100,000 years. Then for the large or early release, it's kind of conditional event. So if you have the core melt, then it's, if you lose the containment too, not only the core, then you can get into large or early or both releases. And for this, for the new plants, the requirement is to be below 1 in a million. And for in a million years, and for the old one is a little bit smaller requirement. It's 1 in 500,000 years. Huh? Now, just to recall that when we are thinking about safety, we think through 3 fundamental safety functions also. So we have to have control of reactivity all the time. We have to cool and we have to confine the materials all the time. This is kind of a mantra I will say a few times and you try to remember. This is an important part of the story. Now to the defense in depth, the Swiss cheese model. If you look at it through the multiple barriers, this is the picture showing you that. So where do you have radioactive materials? Inside the fuel. Is there anything else which is radioactive in nuclear power plant? Yes. What? Coolant, yes, there are some things which are activated outside of the fuel. Spent fuel? Okay, but it's fuel. There are also some things which happen in structural materials, some things which happen in coolant, but this is very little, in principle, very little and very difficult to get out. What you can get out very easily, usually, is some gases or some elements like iodine, cesium, which would be in gaseous state at normal operating temperatures. Iodine with, let's say, well, I think around 180 degrees, and cesium, the next one is about 300. So the fuel elements would be in the order of 400 degrees centigrade. And these are kept inside the ceramic fuel. It's usually porous. It's not fully filled space. It has some caverns, and these gases are kept there as long as it goes. This is the first barrier to keep the gases inside. The solid radionuclides, of course, are trapped even better inside the fuel ceramics. You don't want to get them out. If you melt the fuel, they will go out. Yes, it's spent fuel. If you are lucky, it's still closed and you don't have any problems. That's the what is safe position. If it gets melted, the gases go first, and then the other things. Now, the second is fuel cladding. So the fuel is usually in pellets stuck in a tube. This tube is made usually of zircaloy or some material which is transparent for neutrons. So this is the second barrier. And you want to keep it intact as long as possible. The third barrier is reactor coolant pressure boundary. It's the pressure vessel, the piping. So look at it in this way. If the gases go out of the ceramic fuel, they are kept into the tube. If the tube fails, they are still kept in the reactor coolant within the boundary. If this boundary fails, so this is the reactor pressure boundary, it goes into containment. And usually there are two containments. The first one is kind of leak tight, and the second one is not completely leak tight usually, but still it's better than being in the open air. So you have 5 barriers which keep the materials inside. Yep. Cavitation. Yeah. Now I would say in theory, cavitation can destroy of course, the tube. Cavitation destroys metals if it's serious enough. I'm not sure there is a lot of cavitation in the core. Luckily not, but okay. There are also other ways to destroy it. Like the typical way would still be to overheat the fuel, and then it will melt, and then you start to melt the structure outside. And luckily, the outside concrete will still remain there. This is the drill here. Of course, it can be mechanical failure of anything, which is also. Now, by the way, for the normal operation, typical value would be that 1% of the fuel can be damaged. Now, in Krško, I think there are about 20,000 cubes in the fuel. 1% is a lot. So this is the limitation in the license. They can have about 1% of fuel damaged. The tricky part is that, of course, if you open the first and the second barrier, you get a lot of trouble with radiation materials into the primary system, which is not very localized. It's all over the containment. So then they start to take care of it because they will have to clean everything. It's a kind of natural approach. Okay, And now a little bit more formalized look at the defense in depth. Along with the text in the directive, but this is an older text. It's from the International Nuclear Safety Group, which is working with IAEA, and it was put together in '96. You can get the document there. So the first level of defense is prevention of abnormal operation and failures. How do you do this? Conservative design, high quality in construction, high quality in operation. So you don't want your car to fail or to be corrupt or something like that. That's the first level of defense. The second one is, if there is something wrong, pick it up, control it, mend it. So it's controlling, limiting, and installing protection systems already. So the systems which push the reactor back into the normal state if needed. The third level is control of accidents within the design basis. Now we have a new word, design basis. That's something which was considered in the original design. We'll look a little bit into list of events which were considered in original design to give you some. It was very thought through already in the 50s and the 60s, but so if you know there will be, or if you expect an accident or an event, like you can expect that you would push the button for the control rods to fall into the reactor and they will not fall in. What do you do now? Is there another way to shut down the reactor? Sorry? Boron? You can put boron in. And this is also one of the design principles. You are never left with only one option. There is always another option, at least two of them. Okay, so you have something, and this is called engineered safety feature and accident procedures. Procedures, this is something, the list of tasks for the operator are also there. So the operators can take a manual, say, okay, I'm going this way. I have to push this, I have to push this, I have to put more water in, I have to put less water in. These things are all taught in advance. By the way, the procedures. There was a nice statistical piece of information from the American aviation. So if pilots are trained or they know about certain event, what would you think is the probability to solve the problem? If they are faced with the problem they were trained for or they are aware of it, what would be the percentage of the successful intervention of pilots? Close, 80 plus. And if it's a surprise, less, 7. Procedures, advanced thinking. Well, the pilots, they have less time than the nuclear power plant operators, by the way. So for the pilots, half an hour is a lot of time. For the nuclear power plant operators, half an hour is usually the time which is in the design of the machine, of the old machines. So they don't have to touch. They just look what's going on, and the machine will take care of the first half an hour. That's a fail-safe design. Okay, now, so we were able to control the accidents. If you come out of such an accident within the design basis, it's pretty good chance that you will be able to restart the plant after you figure out what happened and clean up a little bit, okay? Now, there is next level, severe plant conditions, where there is already some accident going on, and then you focus not on, well, if you cannot control, then you try to prevent, and if you cannot prevent, then you go to mitigate. Complementary measurements and accident management. Now, if you are, imagine a situation that there is no water in the Sava River, in the river nearby to the nuclear power plant. What do you do? You need water to chill the reactor. What do you do? You don't have a engineered safety system directly for this. Can you call for the fire brigade? Principally, yes. If they have some water, that water would help you. So here already that could be a significant part of improvisation also there. They have some prepared procedures. If they fall out of these procedures, then it's improvisation. In Fukushima, they were out of electricity. So at some point, the operators started to take batteries from the cars and bring them to change the configuration of the valves in the. So it's battery, it has electricity, it does the job. That's the improvisation part, which comes here in this 4th level. 5th level is emergency response, off-site emergency response. So we decided, okay, we cannot keep it inside, it will go out. So let's inform the neighbors to fly away. Then typically the military or similar to military structures take over the structures which take care of the natural disasters, stuff like that. They will evacuate the people. And this is level 5. This is the thinking of the IAEA in the 96. Now, this is the drill. First control, if you cannot control, prevent. If you cannot prevent, mitigate. If you cannot mitigate, call for help and run. Now, this is another view. WENRA is West European Nuclear Regulators Association. And they did, after Fukushima, they did revisit the table. And you see more or less the same things as the INSAC, but they invented level 3B, which is additional safety features accident procedures. Now, to give a little bit of historic background, before Fukushima, the rule was that machines are resistant to a single failure. So you have one problem, whatever fails, no, you can do it, but it was not really taught what you do if you have 2 failures. So if you have the earthquake and tsunami, that's a little bit out. So here the Western European regulators started to think, okay, now we have combination of events, what do you do? Then it's to some extent the thinking, forward thinking is part of it. So like the pilots, if they know what they're doing, it's there better. And the part of it is also that you can actually sometimes with not too much investments really solve the problem. You can, one of the ideas at that time was really not to call the fire brigade, but to buy the equipment the fire brigade has and have it on the plant or somewhere where you can bring into the plant. So you can get additional water pumps and stuff like that in the game. Okay. So they call it the association. Here we have 2 new concepts which we need to be aware of. One is that the levels of defense are also linked to somehow to radiological consequences, this one. So for the first 2 levels, there is actually no impact on the environment, which is accepted. No radiational consequences outside. Radiological consequences cited. For 3, minor. So 3A and 3B are there still to prevent anything to go out or nearly anything to go out. And in 4, you stay with some consequences to the environment, and yet it's still limited to the amount which don't really call for evacuation or any serious measures. And only the last one is where there is so much radiation outside that you have to evacuate. Now for the generation 4, if you heard about generation 4 reactors, people are thinking how to avoid the evacuation at all, completely. So the idea is to design the machines in a way there will be no evacuation. Now, I think this is a very good idea in principle, and there will be very difficult to convince the regulators that it is so. And I'm not really, personally, I'm not really convinced we have to play. We are part of some international projects now trying to figure out this safety of a few types of generation 4 reactors. We will be looking into this now evacuation possibilities. Also, I'm not yet convinced it's possible, or if the idea is approved. Oh, it's just pre-design. Be careful. This new scale just got a preliminary.
Yeah, but they say that it doesn't need an offsite.
Okay, so they don't need offsite regulation. So the NRC said, okay, we can agree with the idea. Now you show it. They are in the show it situation now. Now they will have to demonstrate that, and we will see what will be the result of this demonstration. In principle, yes, everybody is happy if we go that way. Now to show it, that's another story. Okay, and this is the consequence part of the risk equation, the radiological consequences. That's why it's good to have it here. And there is another associated plant condition categories. So the plant is operating in different conditions in different levels of defense in depth. The first one is normal operation. That's the Venra description. I like the American descriptions more, and I will come to them a little bit later. They tell to me at least a little bit more. Another one is for level 2 anticipated operational occurrences. And we'll look into what events that would be in a few minutes. And then it's postulated single failures or initiating events. That's the old drill. One failure, you survive any failure, one. And that's the new drill, some multiple failures which can bring like tsunami and earthquake. Actually, it was not earthquake, it was loss of electricity and tsunami, which killed them in a way. Earthquake was just a trigger for both. And this is also how you interpret this initiating event. Initiating event in Fukushima definitely was the earthquake, but then the trouble was tsunami and loss of electricity, not earthquake per se. And this is with the postulated cold mare accident. So let's put it this way, up to approximately number 2. I think I have this, yes. 1, 2, and 3A were more or less, or were completely taken into account by the design. Part of 3B and 4 was also taken care of the design, but after Fukushima, there was something which is called design extension conditions, which was invented by, I think, the European, not regulators, but utility, the operators of the plants at some other occasion. So the machines were designed for, there is something which is beyond design. So we said, okay, we don't care about this. It happens, it happens. And now there is something in between, design extension. It makes sense to me for old machines. Like if you have an old car, you will probably not install an ABS. It's too expensive. But if you buy a new car today, it has an ABS. So what do? If you need to get the license if you need it to get the license, then you can invent something called, it's nearly an ABS and put it in the car. It's that type of solution to me. But nevertheless, the regulators are now happy with the design extensions, and they say, okay, the requirement for safety is a little bit larger now, so please provide a solution to that for double failures. That's for selected double failures, not for any. For these which tend to be critical, like again, losing the electricity and tsunami. So also for the Kershko nuclear power plant, this combination was historically pretty important one. they were looking into losing the electricity. They were looking into the not tsunami, but high river levels. And they started to solve this type of problems a little bit before Fukushima. They figured it out without Fukushima. So they made a lot of improvements to the dikes and flood control. And I think there is about 10 or even more than 10 power lines to the nuclear power plant. So the external sources of energy are plenty. There is a specific gas power plant nearby 10 kilometers away, which can be connected directly. So they have diesel generators, blah, blah, blah. So it's a lot of options to do it. Good. Let's try to compare these levels between INSAC 96 and Venra 2013. You will see the first level, it's more or less the same. Venra took a little bit more of the words to describe it. The second one, it's again the same, slight changes in the wording. I would not say it's very important. Now the free, it splits in free A and B. And free B requires additional safety features. This is the change here. Again, 4 and 5 are, well, 4 also requires a little bit more now with the Venra, or a little bit different approach, because in 4 they will the Venra intends to control severe accidents. It was not really meant so at the beginning. Okay, we already touched the plant states or conditions in which the plants operate. And let me take an old American description of the situation here as a basis. So it's based on the American standard, American National Standard Institution and American Nuclear Society provided this one, 51.1 in 83. And it's complemented with some numbers. So they have 5 plant conditions. You remember there were 5 levels of defense, okay? Although the last one was already out. It's beyond the design, the last level of defense. And here are some frequencies of events or which put the plant into these states. Another American institution, American Society of Mechanical Engineers, called those plant conditions as normal operation, upset operation, emergency operation, and faulted operation. If I go to the faulted operation, your only goal here is to shut it down, okay? You will never use it anymore, just to shut it down and go away without any serious consequences. Emergency, you can shut it down and you will repair something, but you can do it maybe 5 times in the lifetime of the reactor, this type of events. And the frequency expected is between 10 to minus 2 and 10 to minus 4 for emergency, and below 10 to minus 4 for faulted. And you see that you come out of design thinking at about 1 per million years. 1 failure per minute or event which causes failure with frequency less than 10 to minus 6, less than 1 in million years. What does it mean here? You can accept this, or people said, okay, whatever the consequences with these events, like I think I mentioned the asteroid yesterday. Whatever the consequences, if a asteroid falls on the nuclear power plant, we don't care. We leave it as it is. But for those with frequencies higher than 10 to minus 6, we provide a defense. Of course, the first one is the normal operation, which is happening every day, all the time, where you don't have to do anything special. So here, again, I'm trying somehow to put different plant operation modes or conditions into the levels of defense. Emergency, has there ever been an emergency in Krško? I don't think so. Emergency as event classified as emergency. Yeah, but that's design consideration. So the designer said, okay, the faulted type of event is once. You just walk away and that's it. You are lucky to walk away, okay? But the emergency is, well, you will have some repairs and the machine might be used again. That's kind of the gradation here. Actually, what we can say about, there was an earthquake in Zagreb in Croatia a few months ago. If I remember correctly, the peak ground acceleration was measured around the nuclear power station. It was I think magnitude 5.5 or something like that in Zagreb, not very far away from the nuclear power plant. The peak ground acceleration which was measured was in the order of 5% of g, and the normal operation of the nuclear power plant is allowed up to, this one was smaller than 15% of g. This is the first level of the earthquake, which goes into the upset. So they consider it a trouble where you can continue operating without any problems. Then you go around, look if there is something, there are some problems, and that's it. And there is another level, this is called operating basis earthquake. There is another level, which is, originally it was about 0.3 G, which is the safe shutdown earthquake. So where the intention of designers was, if there is an earthquake of this magnitude, then we can shut down the plant. And because there are some margins always, you know, engineers, they cannot do it exactly. The guys in Krško, they claim they can survive without any problems up to 0.6 G. And these are horizontal accelerations here. By the way, I think you will have trouble to walk, real trouble to walk if you are faced with the 0.3 G earthquake. And then they claim they can survive with 0.6 G, and probabilistically, even 1 would be survivable, 1 G. Okay? Yeah. You see, 5.5 was. yeah. That's the story. So usually these machines are so resilient that everything in the vicinity will be destroyed and the machine will still be there. But that's also, I think this is the original idea. Hopefully it works.
I had just one question.
Go.
Yeah. Can we hear each other?
Yes.
I had just one question. How would the financial factor of like stopping the factory in case of some upset state, how would it like be taken in consideration whether the factory would be stopped or not?
The question is, how would the financial factors be taken into consideration?
Yeah, yes. Are like financial factors sometimes, are they like, do they, če lahko po slovensko povem, ali kdaj finančni faktori pripomorejo k temu, da se neka stvar mogoče naredi na malo manj varen način, kot bi se sicer, recimo, če bi bilo vse 100% samo po nekaj varnostni logiki?
Okay, thanks. So the question is, would there be a chance that just because of financial reasons, the machine is not done completely well in some respect? In principle, that could happen, let's say, but this is then the duty of the regulator to figure out. You know, the regulator sets what is the acceptable behavior or acceptable technical solution or acceptable level. So if the owner cannot afford to provide such a solution, they should shut down the plant. That's very easy. If they are trying to, let's say, manipulate through it, then the regulator should be able to figure it out. This is the duty of the regulator. They are taking care of you and me as a general public in such a case. And this is why the regulator must be independent of any financial interests. You know, it's not necessary, the financial interest might not be the only one. Sometimes, in some cases, I would say that I would assume that there are some countries where electricity is desperately needed. So if you balance the risks of shutting down the nuclear power plant, or a few of them, and a lot of people losing the electricity because of that, then the picture might be a little bit different. But in principle, we would like the regulator to be independent of this consideration. They say, oh, that's not safe. Let's shut down the thing. I hope I answered this question.
Yeah, it was like, imel sem malo tako primerjavo, recimo trenutno, kaj se dogaja z epidemijo, ne? Ker se mi zdi, da se vsak recimo po svoje določa določene ukrepe, ne? In zdaj tukaj bom rekel, se mi pa tudi recimo, ne vem, da se je nek potres zgodil in da zdaj pa bodo rekli, ok, bomo sklopili ali pa ne bomo sklopili, glede na to, kakšen bi bil finančna izguba v določenem primeru, ne? Ampak ja, se sem približno navedel.
Okay, there was a kind of, let's say, a little bit more explanation to the question and answer. So with parallels to the COVID, where everybody is trying to figure out his or her own rules today. So can this happen also in nuclear safety? Especially in the example of earthquakes, I would say no, because the numbers are known in advance. So it's not like now, okay, earthquake happened, let's figure out what does it mean. No, we know that we can operate until 0.15 G. So if we measure less than 0.15 G, that's fine. If we cannot, because it's known before. And I think this is also one of the important principles of safety behavior. You have criteria and goals set upfront, because when you are in trouble, you never have time to figure out what's good and what's not good. Have it before, and be a little bit on the safe side. That's the drill here. So you stop the things when your criteria is out, and then stop and think, what do we do next? If you rely on real-time rules, like in COVID, now they are telling to us every day something new. That's not a very good safety perspective, but might be acceptable in the case like COVID, which is still, well, after 6 months, is it new or is it not new? We could debate it, but after 6 months, at least, I think the limit of the immunity is about 6 months. Even if we could be immune after being infected, we only know for about 6 months time, not very much more. It's the limitation of the knowledge. Okay, let me touch some examples of events, and I told you have the slides already in the repository, so you can look also a little bit deeper. Plant condition 1 with frequency 1. So this happens all the time. Startup, shutdown. Well, startup, shutdown does not happen all the time, but it could. Technically, it's a normal, completely normal event. Nothing exceptional in it. Shutdown, refueling, hot standby. Hot standby is zero power, but reactor at the temperature, at the full temperature. And power operation, sometimes they follow the load or something that's completely normal stuff. Now, the 10% frequency, plant condition 2, it's already a little bit of trouble. Inadvertent control rod withdrawal, 1. Partial loss of reactor coolant flow, like you have 2 loops, 1 pump goes out. It's already tough 1, but okay. Partial loss of safety-related cooling. For example, you lose 1 out of 2 or 3 different trains. Reactor trip. It's not to be. That's when the reactor scrams automatically. It's not to be done every day, but that's still not a very, very difficult event. Also, turbine and generator trip. Loss of feed water flow and single operator error. This is something which is expected with probability of 10%. And we go on like, well, not really nothing happened, but machine is, in some cases, with reactor trip, it's definitely not running anymore, but it's still okay. You look what happened and you go back to the power and that's it. That's a little bit more tricky already, but still within 1%, losing all the power from the outside. Having primary containment spray actuation, it can actually make an under pressure in the containment and break your containment, which is not very good one. Minor fuel handling accident, it's radiation pollution in the plant, more than anything else. Complete loss of reactor coolant flow, but you still have the coolant. It's just all the pumps stopped. So it's trouble. You shut down the reactor, but you survive it. Rupture of 1 steam generator tube. There are about 4,000 or 5,000 steam generator tubes per steam generator. So it's not, 1 steam generator tube is usually what, 3/4 of an inch. So like pipe work in the plumbing in the house. Well, safety, it's a safety problem because you breach. Yeah, steam generator needs a lot of heat transfer area. So you do it by having a lot of small tubes. So you put about what 100, well, more than, it's about the size of football field of the heat transfer area in 1 steam generator, which is not so big, it's not so large. Okay, then those between the percent and 10 to -4, small loss of reactor coolant. Drop of single spent fuel assembly, that's a radiation damage, also pretty serious. Leakage from spent fuel pool in excess of makeup capacity. So you will be out of water in a week, in trouble in about, well, less than a week. Blowdown of reactor coolant through multiple safety or relief valves. You know, it's a trick that if you have pressurized equipment, you have to have safety valves on it. So a reactor coolant system has safety valves. If the pressure is too high, you will lose the fluid to protect the pressure boundary, but you're also losing the coolant. So it's event which is tough, but it's still okay. And these are typical events where you shut down the plant for good if it happens. Large reactor coolant accident, which usually assumes that the primary pipe will rupture. So you try to cool the reactor, and then that's it. Single control rod ejection is also there. Drop a spent fuel assembly onto other spent fuel assemblies. That also happened in Fukushima somehow, not really fuel assembly on fuel assemblies, but some parts of the structures on the fuel assemblies in one of the spent fuel. So there you are in trouble. Not in a trouble, you cannot shut down the plant, but you are in trouble because you have to stop the operation. There is a nice summary of all this, which I will leave for you in the slides. So the International Nuclear Safety Advisory Group tried to put operational state of the plant, level of defense, objective, essential features, control, procedures, response, condition of barriers, so which barriers fail, in one single table. So you have level 1, level 2, green is normal operation, blue is postulated accident, so it's accident, somebody assumed it will happen, and red is emergency where you need to improvise a little bit. This is now a summary of everything we tried to say. With this, I think we can skip the design principles. They will come back next week. And let's just summarize. There are 5 or 6, how you count, levels of defense on depth. They result in different radiological consequences. Actually, the up to 3B, we don't really want to have any significant radiological impact. 4 and 5 are a little bit, well, 4 is a little bit of radiological impact, and 5 is really serious radiological impact. The first 3, 1 to 3A, are called usually design consideration. They are in part of design considerations. For the new one, for the new reactors, design and design extensions can be packed into the design. Of course, before you design, you can put everything you need. But design extension is a category for the old machines to be brought to the today's standards. And then there will always be something which we didn't consider in design and will be beyond design. The question is only if we can live with the consequences or how it compares to the other risks we have in the life. If I go back to this one, that maybe, can you imagine today, life today without electricity? So we were chasing the only plug. We cannot even have a lecture without electricity today. So what is larger risk then? A little bit of radiation or being without electricity? I leave it with you. Or how much radiation is better than being without electricity? I leave it with you. Maybe you'll answer to me next time or during the exam. That could be a nice exam question. Thank you. See you then next week.